Okay, before we start our regular lecture, I just wanted to bring another way to look at why dislocations prefer to move in close packed directions and close packed planes. Yesterday we have seen that physically why should they move it, but we can also look at a mathematical expression and then get convinced. So this is the expression. So this is the expression for Paul-Nabarro stress. In the previous class we have given this expression, but this is equivalent to this expression where W is the dislocation 4 bit. Okay. So here it is pretty clear, your A is your interplanar spacing and B is your interatomic spacing or Burgers vector in the mother, right, in the direction of the slip, whatever is the interatomic spacing, right. Now if you have your so for instance, this is what is this tau p? That is the stress required to cause slip by dislocation motion, isn't it? That is what we have discussed in the last class. Tau p is the stress required to cause dislocation motion, which happens to be much smaller than the shear stress required to cause slip by glide of a plane of atoms, right. All the atoms in the plane should be moved at once, vis-a-vis moving, causing slip by moving the dislocation, right. This is the stress required to cause slip through dislocation motion. Now if this is your interatomic distance, right. If this becomes smaller, what happens to tau p? For a given interplanar spacing, let us say A is given, in that interplanar spacing you should choose the minimum B such that this becomes minimum, right, because negative is there, right. So the minimum value of B will give rise to minimum value of the shear stress required to cause the slip, and that is the reason why the dislocations prefer to move in the close packed directions, because in the close packed directions the interatomic spacing is minimal. Is that clear? No? Still sleeping. Yeah. So in the close pack, what do you mean by close packed direction? The atoms, neighbors are touching each other, right? If it is not close packed, they will be something like that. So the interatomic distance between two neighboring atoms, right? The distance between two neighboring atoms will be minimal when this is close packed. Why that should be minimum? If that is minimum, then your tau p will be less. If you increase the value of B, what happens? Then the tau p increases. What is the meaning of that? That means the stress required to cause slip is going to increase, right. So if you want to cause plastic deformation or slip with minimum stress, the best bet for you is to choose a direction in which B is minimum, and that happens to be in the close packed direction. That is why dislocations prefer to move in close packed direction. Fine. Now look at interplanar spacing. For dislocation, for again this guy is to be minimum, A should be, with increase in A, tau p reduces, isn't it? When does the A increase? The maximum value of A will be, the A increases, A is the interplanar spacing, that will be maximum for close packed planes, right. If you take two close packed planes, their interplanar spacing is going to be maximum, right. Since that is going to be higher, the higher value of interplanar spacing can be obtained between close packed planes, and that leads to lower Paul-Nabarro stress, and hence that is also another way to say that dislocations prefer to move in close packed planes. Is that clear? Okay. Still not clear to some people? I still see some blank faces. So in the last class we have derived the expression for resolved shear stress tau r is equal to sigma cos p cos lambda, where phi is the angle between the direction of the application of the load to the normal to the plane on which you are actually resolving, on which you want to find the critical resolved shear stress, and lambda is the angle between loading direction to the slip direction. Okay. So, once you have that information, then this you have this geometric factor called cos phi cos lambda, and which is called Smith factor, right. So, for a given applied stress, if you want to cause slip, you might want to have resolved shear stress to be maximum for a given sigma. If you have your, how can you make your resolved shear stress to be maximum? By playing with phi and lambda, right. So, for different orientations of slip plane, that is described by phi, you are going to get different resolved shear stresses, and again for a given phi, different slip directions will give you different resolved shear stress. So, if you want to cause slip, all that we require is the critical resolved shear, the resolved shear stress to be equal to the material property called critical resolved shear stress. When these two become equal, that is when you initiate slip, right. So, that means slip can get initiated on any of the slip planes, on any of the slip directions, on which, along which you will have your resolved shear stress to be maximum, right, typically, because with the same sigma, one of the slip planes and one of the slip systems will result in maximum resolved shear stress, and when you have a maximum resolved shear stress, that is going to be close to your critical resolved shear stress, and naturally that is the slip system which will be subjected to initial slip. Is that clear? You will cos phi cos lambda is going to be maximum, right, for phi equal to 45 degrees and lambda equal to 45 degrees, and then you will have your maximum resolved shear stress for a given sigma, and that is typical. That is the reason why you will see the, if you see the slip bands, they are oriented at 45 degree plane to the loading direction, and the loading direction is uniaxial. Alright. So, this is something that we have seen yesterday, this problem, we have solved it. Okay. So, now having understood the concept of resolved shear stress and how one would impart slip, or in other words plastic deformation in a single crystal material by increasing the load or by playing with the geometry. That means you do not have to only increase the magnitude of the load by changing the direction of the load, so that your phi and lambda are going to get varied, and that is how you can also impart slip with the same magnitude, right. And now let us try to understand. So, the next module that we are going to study is going to focus on the mechanism of slip in cubic single crystal material. So, how does plastic deformation actually take place in single crystal material? What are the different phases of plastic deformation, and what is the role of grain boundaries on dislocation motion, and explain how can we explain the strength of nanocrystalline materials compared to their coarse grained counterparts, that we will discuss, and then we will have to discuss about different kinds of strengthening mechanisms and why materials become harder or strengthened after plastic deformation. And this is something that we have also discussed, that the tensile strength, yield strength and percentage of elongation of a solid solution change with the percentage of solute atoms, right. So, you can actually see how the percentage of alloying element of nickel in copper nickel system is going to change the mechanical properties. So, and then calculate and compare the stored energy in dislocations and total deformation energy in a material. What is the meaning of that? That means when you are applying a load, how much of the energy that you are putting in is actually going to dislocation, and what is happening, what fraction of that energy is going to be responsible or going to help the dislocation motion, and what happens to the remaining fraction, right. So that is something that is important to understand. Okay. So this is a typical shear stress, shear strain plot on a single crystal material. Let us say this is typically the kind of stress strain response of a single crystal FCC material. BCC and HCP may also show similar behavior, but some of the stages are not going to be as prominent as we see in FCC. So we are restricting ourselves here to the FCC material, but qualitatively the figure looks almost similar. Okay. And here you have a FCC material, and this plane shown in light green background is your 111 plane, and the 3 directions shown in the red color are your 110 direction, family of 110 directions. And the reason why we have shown them here is because in FCC material, that is the closed pack plane and those are the closed pack directions. That is why we have shown. Okay, all right. So in a single crystal material, you have basically 3 stages of plastic deformation: stage 1, stage 2, stage 3, preceded by the initial elastic deformation. So when you are applying a load on a crystal lattice, the first thing that you will do is actually to stretch the bonds, isn't it? So that stretching of the bonds is actually your elastic deformation. As long as you are not breaking the bonds, the moment you remove the load, the system comes back to its original configuration. Only when you break the bond, then it will not be able to come back to its original configuration. That is what we are calling plastic deformation. The breakage of bond through dislocation motion is what we have seen as slip, and that is nothing but plastic deformation. Okay. So if you have a cubic crystal, and we know these cubic crystals have many slip systems and typically greater than or equal to 12. In FCC you have 12, BCC 48 and HCP 12. However, in FCC the 12 slip systems are primary slip systems. In BCC you have 12, 12 and 24, right? The first 12, that is 110 plane and 111 direction. It is the other way around compared to BCC and FCC. FCC the closed pack plane is 111 and closed pack direction is 110. In BCC 110 is your closed pack plane and 111 is our closed pack direction, right? So that is your primary slip system, and remaining they are 12, right, and remaining 36 are secondary slip systems. Similarly, in HCP, the basal plane, the first 3 slip systems are the primary slip systems and remaining 9 are secondary slip systems. Okay, whereas in FCC all the 12 are primary slip systems. All right. So the initial elastic strain is, as I mentioned, is due to stretching of bonds, or it is described by Hooke's law that we are all familiar with. And the stage 1 is also called easy glide. And this point what we call is yield point. What is happening? By now you have your resolved shear stress has reached critical resolved shear stress on one of the slip systems. And there is only one slip system, that is one active slip system. When we say active, that means there is plastic deformation happening, taking place on that slip system, right? So yield point and easy glide, that is only primary slip system is active. Okay, and hence once you impart, and that becomes easier at the almost at constant stress. It is not constant, it is slowly increasing, but almost at constant stress you will be able to impart large strain. And that is called easy glide, because you are not required to put in additional effort. Once you are here at almost at the same stress level, you are able to cause plastic deformation. That is why it is called easy glide. And the stage 2 is interesting. So when you are causing plastic deformation, when you are loading the system, when you are causing plastic deformation, there is going to be some permanent deformation. As a result, you are actually changing the orientation of the crystal planes with respect to the loading direction, right? So, since you are changing the orientations, the slip system on which initial plastic deformation took place, and it is possible that that is not going to be your favorable slip system anymore, some other slip system is coming into activity, right? So, the new slip systems are getting activated. So, at the onset of stage 2, you do not have one slip system, there may be other slip systems getting activated, which means it is not one, the dislocations are not moving in one plane, but in different planes. Even within one plane, you may be increasing the density of the dislocations, and as a result, what happens? If you have one dislocations, this guy happily moves. So, imagine this example. We have discussed about the carpet example, right? So, when you create a hump, and then you can easily move the hump towards the end to cause unit slip. Now, you create a hump here. Imagine the carpet is big, and some of your friends goes to middle of the room, and then they create a hump in other direction. You have a hump here, and there is a hump there, and both of you are moving like that. Then what happens when they meet? So, you are actually able to cause plastic deformation with certain stress. When they meet, what happens to the amount of load that you need to apply? The stress will be the same, or you need to increase? Are you able to do this thought experiment? Will it increase or decrease? Louder please. Huh? You can actually do that also. You must have encountered when you are also doing that with paper also, you can try, right? You can create a hump here and then other side and then move, and then this guy is in one orientation and this guy is another orientation, and they sort of entangle, right? And then they provide resistance to further motion. That means these dislocations are interacting and they stop, they hinder the dislocation motion. They do not stop, but they hinder the dislocation motion, and then what you need to do? You need to put in more effort to overcome that obstacle or overcome that resistance, and then you continue the dislocation motion. But by this time, you already have applied sufficiently large amount of stress, resolved shear stress, which means it is very likely that several dislocations which are in parallel planes or in other planes, the dislocation in one plane moving this way and the dislocation is moving and both of them are intersecting. So, the dislocations on different planes can intersect, dislocations on the same plane can intersect, and all of them going to hinder further slip. And hence, in order to continue the plastic deformation, you need to apply higher and higher value of stress, and that is what is called hardening. That means your material is becoming harder to cause plastic deformation, and hence this response is called hardening response, or it is also called work hardening, right? By doing work, the material is getting harder and harder. Is that clear? Yeah. So, this is primarily because the interaction of dislocations within the planes, slip plane, and within planes parallel to each other and across the planes which are not parallel to each other, right? You are going to have this sort of crazy interactions, and that is what leads to. And then stage 3, okay, the stage 3 of the plastic deformation in a single crystal material is, this is typically the final stage. So, here the amount of resolved shear stress is so high that it can overcome all the obstacles. You really don't have anybody to stop, because your force that is applied or the stress that is resolved shear stress that is experienced by each and every dislocation is much larger, or the locks that are the dislocation locks experience much larger resolved shear stress, so that will not be able to stop the plastic deformation, right. So, that is usually the stage 3, and that usually stage 3 is followed by fracture of the specimen. Eventual around at the end of stage 3 you will have eventual fracture of the specimen. So, that is how the plastic deformation followed by fracture happens in a single crystal material, and this is typical for cubic crystals, and this diagram is more relevant to FCC materials, although you will observe similar stage 1, stage 2, stage 3 in BCC and HCP materials, but the extent of stage 1 is going to be very small for BCC, because there are so many number of slip systems in BCC. It is possible that the other slip systems are also getting activated. Because of the existence of more number of slip systems, other slip systems get activated, and as a result you will have stage 2 kicking in much earlier. Okay? Alright. Any questions? Okay, how do these dislocation interaction happen? We said the stage 2 or the work hardening stage is due to interaction between the dislocations, right. So, they interact and then they stop each other, or they enhance the dislocation motion, all sorts of things can happen. So, typically the dislocations operating on same slip system might interact, as I mentioned, and they possibly inhibit dislocation motion. How do they inhibit dislocation motion? So, for instance, similar sign dislocations, what do they do? So, there is one dislocation, another until now they are moving like this, and now if they are same sign, what happens if you apply further slip? They cannot move, they cannot come closer, because the stress fields around them will force them to repel each other. And opposite sign dislocations, if they are coming together, what happens? They annihilate, they become perfect, and then what happens? There is no dislocation at all. So, there is no plastic deformation, you cannot cross slip, you are actually going from a imperfect crystal to perfect crystal. So, how do the dislocations combine? How do they decide whether they want to combine or not? Will they always combine or will they not? Let us see. So, it has to be, if the two dislocations has to combine or do not choose to combine, should be depending on the energetics. So, if two dislocations each of Burgos vector of B1 and B2, right? So, the energy associated with the first dislocation is proportional to B1 square, and the second dislocation is B2 square. So, the total energy is this. When they are combining, the resultant dislocation will be B1 plus B2, isn't it? So, the energy of the resultant dislocation will be B1 plus B2 whole. If this energy happens to be less than or equal to this energy, only then the dislocations combine, otherwise they don't, or only then they will interact, they will form a new dislocation, otherwise they won't interact. So, if you see this, if the dislocations are of opposite sign, then what happens? When the dislocations are of opposite sign, always this quantity is going to be smaller than this quantity, isn't it? And that is the reason why when two dislocations are of opposite sign, they nicely combine. But if the dislocations are of the same sign, then this quantity is going to be larger than this quantity, and hence they have no option but to repel. And so that is about dislocations in the same slip systems. You can also have dislocations on different slip systems interacting, and sometimes what happens is when these two guys in different slip systems coming together, and it is possible that the resulting slip system, so when this is one slip system and this is another slip system, the dislocations are interacting. If they have to continue to interact, they should be working on a resulting slip system, and that resulting slip system may be a may be an invalid slip system. What do you mean by invalid slip system? What is the meaning of invalid slip system? Such a slip system cannot exist in this material, both from the planar density, close pack density and close pack direction perspective, right? So that is not going to impart further dislocation motion by working in that slip system, and hence that means the dislocations now don't know what to do, and then they get locked, right? And like in the carpet example, one hump going from this side, another hump coming across, not in the same plane but in a different direction, they get locked. And if you want to overcome, what you need to do, you need to apply higher stress to break open the lock, right? Until you break open the lock, you cannot continue further plastic deformation, right? So that such a lock is called Lohmer lock, and you need to apply higher stress in order to break open that lock to cause further dislocation motion. And cubic crystals have many slip systems, as we have discussed, and hence typically they have very high probability of inhibiting slip, leading to the stage 2 deformation. That is why the stage 2 is characteristic of cubic single crystals, wherein the dislocations interact with each other and cause work hardening.